Hey there guys, in this video we'll be reviewing the concept of linear inequalities. A linear inequality, if you remember, is similar to a linear equation except we're using an inequality symbol like a less than or a greater than sign as opposed to an equal sign. So an example of that would be the inequality y is greater than or equal to negative 2x plus 9. If I gave you that inequality and then I asked you to determine which points satisfy the inequality, we would do that by plugging in the x and the y value given. So for A here, I've given the 0.74. This is a solution if I can plug in 7 for x and 4 for y and get a true statement to this inequality. So let's see if that works. If I plug in those two numbers for x and y, I get 4 is greater than or equal to negative 2 times 7 plus 9. And then if I simplify the right side, I end up getting the statement 4 is greater than or equal to negative 5. That is a true statement, so yes, 7, 4 would be a solution of this inequality. Negative 1, 3. Do the same thing, plug in 3 for y and negative 1 for x. And I get 3 is greater than or equal to 2 plus 9, 3 greater than or equal to 11. Well, that is a false statement right there. So this would be a no. The ordered pair negative 1, 3 is not a solution to this inequality. C, 10, negative 5. If I do this, I get negative 20 plus 9 on the right side, so I get negative 5 greater than or equal to negative 11. Negative 5 is greater than or equal to negative 11, so that is a yes for being a solution to the inequality. We can also set up word problems with inequalities. If I look at this one here, it says John sells t-shirts. Plain shirts cost $5 and graphic shirts cost $7. In order to match his product costs, he must make at least $1,200. So just like we do word problem equations, we can set up this word problem with an inequality. My variables in this would be the number of shirts, the plain t-shirts, and the number of graphic shirts. So I could let P equal number of plain shirts, and I could say G is my number of graphic t-shirts. Well, if plain t-shirts cost $5 a piece, then we're making 5 times P from the plain t-shirts. Graphic shirts, $7 a piece would be 7 times G for their the sales we get from those. If we have to make at least $1,200, at least is a phrase that represents greater than or equal to. The total amount must be greater than or equal to $1,200. So this would be my inequality here. Part B, if he sells 150 plain shirts and 60 graphic shirts, will he be able to cover the product costs? So we're plugging in for P, a 150, and for G, a 60 to the inequality we set up here in part A, and we're seeing if we get a true statement or not. So this would be 5 times 150 plus 7 times 60, and we're determining whether or not that's greater than or equal to 1,200. So if we do this, we get 750 plus 420. 750 plus 420 is 1170, and 1170 is not greater than or equal to 1,200, so that answer is a no. Part C says if he sells 90 graphic shirts, what's the minimum number of plain shirts he must sell to break even? Break even means that his sales are equal to his total costs. So this just means we're going to take our inequality up here and we're going to make it an equation. 5P plus 7G equals 1,200. If these two sides are equal to each other, then his sales have equaled his total expenses and he has broken even, meaning he hasn't lost money nor has he gained money. This is saying that G is equal to 90. The number of graphic shirts equals 90, so I'll replace G here with a 90, and we will now solve this equation for P. So 5P plus 630 equals 1,200, and when I solve this equation, I get P equals 114. So this means that he must sell 114 t-shirts, plain t-shirts, in order to break even. If he sells more than 114 t-shirts, he's going to make a profit. If he sells less than that, he's going to have a loss. Okay, so that's a little bit of review of inequalities. Now we're going to talk about how to graph linear equalities on a coordinate plane. To graph them, it's a basic three-step process. First of all, we want to put the inequality in slope-intercept form, and we need to remember for inequalities, we have to flip the inequality symbol if we multiply or divide by a negative. Step 2, we graph the line. If we have less than or greater than symbols, we use a dashed line, and if we have the equal to bar underneath, we use a solid line. And then step 3, we shade. For greater than or equal to symbols, we shade above the line, and then less than or equal to, we shade below the line. So on the back, example 1, y is less than or equal to 2/3 x minus 1. This is already in slope-intercept form, so we can go ahead and we can plot our points. Y-intercept is at -1. Slope is positive 2/3. So our points are going to do this. We need to think about what kind of line this is that we're going to use. Okay, this is a less than symbol. There is no bar underneath, so this is going to be a dashed line that we use to connect these points. And we need to think about the shading. This is a less than symbol, so that means we're going to shade below our line. So the shading will look like this. Okay, number 2, 5x plus 3y is less than or equal to 12. I need to change this equation to slope-intercept form first. So I need to subtract 5x from both sides to get negative 5x plus 12, and then divide everything by 3. I end up getting y is less than or equal to negative 5/3 x plus 4. So I'll make my points first. Okay, let's talk about what kind of line we have. This is a less than or equal to, so because of that equal to bar, this is going to be a solid line. So I need to connect my points just with a regular solid line. And because this is a less than symbol again, this is going to be shading below the line. And so below the line for this type of line would be in this direction here. Let's talk really quick about what this shaded region means. This is just giving us all of the ordered pairs that are solutions of this inequality. So if I were to pick any ordered pair from this red shaded region and plug it into this inequality, I would get a true statement, just like we did for the A through C examples here. If we had graphed this inequality on a coordinate plane, the points 7, 4, and 10, -5 would have been in the shaded region. And then any point not in the shaded region, for this inequality here, the point -1, 3, for example, would give us a non-solution. So any point up here for this particular graph would be a non-solution. Points on the line, if you have a solid line, they will give you true statements. If you have a dashed line, points on the line will give you untrue statements. Okay, so that's what all the shading and solid and dashed lines really mean. They just give you a visual representation of what the solutions are for these inequalities. Okay, number 3, x minus 6y less than -12. So putting this in slope-intercept form, I have -6y is less than -x minus 12. And then I need to divide everything by -6. When I divide by a negative, remember my inequality sign flips. So this becomes y is greater than 1/6 x plus 2. So we have a dashed line for this one. A greater than implies a dashed line, so I'll connect my points with the dashes. This is a greater than symbol, so we're going to shade above the line. And then, of course, any point in this red shaded region would give us a solution for this inequality. Okay, number 4, x is less than -4. Remember the x equals equations give you vertical lines, so this will be a vertical line through an x-intercept of -4. So 1, 2, 3, 4 right there, -4, 0 at the x-intercept, and then this is going to be a dashed line, dash vertical line that will go through that x-intercept of -4, 0. For vertical lines, we don't shade above or below vertical lines, we shade left and right. So because this is a less than sign, we're going to shade to the left of this line. So it's going to be everything in this direction. And this will be our shaded region. Okay, in this last example, we have another word problem. It says Stephanie makes $12 per hour babysitting and $8 per hour working at the grocery store. She will need to make at least $600 to buy a new computer. So part A wants us to write an equality to represent this situation. So just like the word problem we did at the beginning, we need some let statements. We could let x be the number of hours babysitting. And then y could be the number of hours at the grocery store. So for this problem, our inequality could be 12x plus 8y is greater than or equal to 600. Again, that phrase at least means we need a greater than or equal to symbol. Part A also wants us to graph this inequality. So to graph this, we need to put this inequality in slope-intercept form. So that's going to be 8y is greater than or equal to -12x plus 600. And then if I divide everything by 8, I get y is greater than or equal to -3/2 x plus 75. So I'm now going to graph this on this coordinate plane here. Because this is a real world problem, okay, we're not going to be dealing with negative hours or negative amounts of money, so I've only shown quadrant 1 here on the coordinate plane. Okay, so that's the part we're going to be focused on, is just quadrant 1, where x and y are positive values. So on the bottom of this graph, we can put the hours babysitting, since that's our x values. And then on the side of the graph, we can put the hours spent at the grocery store, since that's what we made y be. And now let's think of a good scale for this problem here. If we go by 5s, that should be pretty good to get us the y-coordinate to show up on this graph right here, and that's a pretty good idea for number of hours worked in a week. So here's 5, here's 10, 15, 20, 25, 30, so every second mark is going to be a 10. Okay, and then we'll do the same thing on the y-axis. So first mark we're at 5, second mark 10, 15, 20, 25, 30, etc. Okay, so to graph this, I need to start my y-intercept, which is 0, 75, so that's going to be up here. And then my slope is -3/2. So it doesn't matter what my scale is. As long as my scales are equivalent to each other, I just need to go down 3 spaces and write 2. And down 3 and write 2. And just keep doing that. And here is my graph, okay? Notice we can't work less than 0 hours babysitting, and we can't work less than 0 hours at the grocery store, so that's why I have not extended the graph beyond these points. Okay, these are the minimum and maximum, these are the minimum, y and x values that we can work. This is a greater than or equal to symbol, so we need to shade above this line, so we're going to shade this direction. So let's think about what this means for this problem. Anything in this shaded region, any ordered pair, represents the combination of hours that Stephanie could work both babysitting and at the grocery store and make at least her $600. Okay, anything in this red region here. Anything below the line in this white region that's not shaded, if she works those amount of hours, she's not going to get the $600 she needs to work at the grocery store. So part B asks us, using our graph, to give two possible combinations of the number of hours Stephanie can babysit and work at the grocery store to ensure she can afford her new computer. So I just need to find two ordered pairs that on this graph would make this inequality true. So one ordered pair I might pick could be this ordered pair right here. Okay, this point 70, 0, that's in my shaded region. Okay, that's just saying that Stephanie could babysit for 70 hours and work at the grocery store 0 hours, and that would give her enough to make her $600. So that's one possibility, 70 hours babysitting and 0 at the grocery store. Okay, let's think of another possibility. Let's find one that's actually inside the shaded region. So I could go to this point right here. This is in my shaded region, and this is the point 30, 35. And so what that means is that Stephanie could work 30 hours babysitting and 35 at the grocery store, and she'd also get her $600. So lots of different possibilities for part B's answer. As long as you give me two ordered pairs that would make that inequality true, then you're good to go. Okay, if you had any questions over this video, be sure to write those down so you can ask those the next time I see you in class. Until then, folks, have a nice day. You're all wonderful people.